Hey guys, this lecture I'm going to talk some about binomial regression models, how to build a binomial regression model using generalized linear models, and some of the common link functions that we use on generalized linear models. The logistic or logit link function, the Probit link function, and the complementary log-log link function. So this should give you a good introduction to how to build a generalized linear model. And then in the future, we'll talk about how, as a Bayesian, you can bring in Bayesian tools to help with this, and some data sets that can be helpful to look at for understanding binomial linear models. So here we go. We're going to start out by discussing binomial regression models. So let's get into that. To begin, let yi I in 1 to n be a vector of response observations. And for binomial regression, specifically, we'll have yi is binomial ni pi. And further, we'll let xi, I again in 1 to n. Yeah. Let me change this up a bit. Let's do, instead of yi binomial ni pi, let's do that ki pi. So we've got some different indices for counting. Xi, I've got n binomial data points with y, and xi are going to be covariate vectors associated with each of my binomial response variables. So the way we usually handle this from a regression standpoint is we do something called a generalized linear model. A generalized linear model looks a lot like a regular linear model, but it has a bit of a different type of structure to it. And give me just a second here. So let's take a look at that structure real quick. So a generalized linear model has 3 parts. The first part is an exponential family of probability distributions that we're going to use for the response variable. The second element of a generalized linear model is something we're going to call a linear predictor. So we've got this x data. We want to be able to relate our x data to our response data. We want to be able to relate our covariate data to our response data. So element number 2 here is and we'll usually use eta here to represent x beta. And so this is the x matrix times the beta vector, same thing you get out of a normal regression model. So that's element number 2. Element number 3, well, we've talked about what y looks like. We've talked about what we're going to do with x. Now we need a way to connect them up. And we do this with something called a link function. And I'll call this link function g. This link function g has to have a particular property for this to be a generalized linear model. And that property is the following. The expected value of our response data y, I'll do a yi in here, given our covariate data, our predictor data x, this guy is going to have some expected value mu, and that expected value mu we're going to be able to express as G inverse of eta, or G inverse of x beta. So what does this look like? For binomial regression. Well, first of all, we need our probability model. Our probability model is yi is distributed binomial ki and pi. Pi is going to be the probability of a success on this random variable, right? Now, often we only have one observation for each covariate set, but we can change that up with the ki. So let's skip down to 3. 2 is basically just telling us that we've got an x beta in here. And so the expected value of yi given xi in this case is going to be ki times pi, correct? So I need some way to relate ki pi to our x beta vector. And we have 3 common link functions for relating x beta to p in binomial regression. The first of these link functions is something that we call the logit link function or the logistic link function. So back over to brush. So what do we need here? We need some function relating pi to our xi beta. And so previously we have stated that ki pi should be some g inverse of xi beta. So let's write that guy down. G inverse of xi beta is going to be equal to, I'm going to give myself a little bit of space here. Actually, I can just write it here. So I want ki times my probability pi. So what's my probability pi going to look like? In this case, I write e to the xi beta over 1 plus e to the xi beta. And we'll talk about this function a little bit more in a minute or so. But this is what this piece here, let me this piece here is what we call a logistic function. So this is where that name logistic regression comes from. So if I've got g inverse of xi beta equal to this guy, well, now I also want to talk about the function g itself. And g is a function of, let's call g a function of pi. And this is going to be, normally you don't have this ki, 1 over ki guy in here. I'm doing this so that I can do general binomial regression with different sample sizes. Often we'll just talk about a binomial observation having its own covariate set. But this is going to be, how do I invert this logistic function? I do it with the following. ln of pi over 1 minus pi. And so pi, remember, is the probability that we get a success on a binomial, on a Bernoulli trial in this binomial. And so pi over 1 minus pi, this guy is my odds ratio. Or this guy is my odds, sorry, my odds. And when I take the natural log of the odds, that is something that we call a little bigger than I wanted that to be. Go back down a step in size here. Okay, that is what we call, what are you doing? Yay, technical difficulties. Oh, I think I keep changing my eraser size. Okay, I want to go to brushes. Here we go. This is what is called the logit function. And so that's why I said we call this either logit or logistic regression. The logit function is this natural log of the odds guy. The logistic function is e to the x beta over 1 plus e to the x beta. So let's think a little bit about how these guys work. And then I will show that these are inverses of each other. So starting with the logistic function. Let me bring back up my red here for a second. What is going on with that e to the xi beta? Well, e to the xi beta is going to grow pretty fast as xi beta grows pretty fast. So if xi beta is negative, e to the xi beta is going to be 1 over the positive version of that negative number we've got. So e to the 0 will be 1, e to the 1 will be e to the negative 1 will be 1 over e, which means if xi beta is 0, what is the logistic function going to look like? Let me ask that again. If xi beta is 0, what is the logistic function going to look like? Well, if xi beta is 0, then e to the 0 is 1. I've got 1 over 1 plus 1. So whenever xi beta is 0, the probability of a success is going to be 1/2. If xi beta is 1, then I'm going to have e over 1 plus e. E is a little bit less than 3, so we're looking at something close to 3/4, about a probability 0.75. Now, what if we go the other way? What if we have e to the negative 1? What if xi beta is negative 1? If xi beta is negative 1, then that numerator is 1 over e, so it's basically 1/3 over 1 plus 1/3. So that's basically 1/3 over 4/3. Let's lose the third. That's 1 over 4-ish, in which case we're looking at a probability of success of about 0.25.
And so that's how this logistic function is going to behave. When xi beta is 0, probability of success is about 1/2. When xi beta is 1, probability of success is about 0.75, -1 about 0.25, and the logistic function, let's switch over to blue. I will do some erasing here in a second. This is something that we call a sigmoid function. We call it that because it has an S shape to it. So I'm not going to worry too much about what's going on my x-axis, but up here I'll have 1, and obviously this is 0 because this is where my axes intersect. So a sigmoid function is going to look something like this. It's going to be monotonically increasing, and it's going to asymptote at 0 and at 1. So as x beta gets very small, the probability is going to get closer and closer to 0. As x beta gets very large, probability is going to get closer and closer to 1. When I say x beta gets very small, I mean it's going to get very negative. It's going to get large in the negative direction. Okay, so this is how the logistic function looks. Now, like I said, I want to show you guys that these are, in fact, inverses of each other. So let's go back over to black. I want to know are these correct inverses? Now, how would I check if they're correct inverses? I would need, let's do this in the way that's going to be easy. I would need to apply both of these functions and see that they effectively cancel out and go back to identity. So let's do g of g inverse. I think that's going to be the way to do this. G of g inverse of xi beta is going to be equal to 1 over k. Now this is where I'm worried I might have done something a little wrong. Yeah, that 1 over k is not where it should be. So I want... Okay, let's take a look at this and see where it goes. Like I was saying, normally the k's aren't in here. So let's ignore these k's for the moment and then see what happens. And then I can pop the k's back in later if I want, though I may just leave them out because this is the way that we usually see this done. So g of g inverse of x beta, that's going to be ln of, now pi is what we're getting now from g inverse of x beta. So ln of g inverse of xi beta over 1 minus g inverse of xi beta. And that's going to be ln of, this is going to be a fairly large fraction now. G inverse of xi beta gives me e to the xi beta over 1 plus e to the xi beta. And now here I've got 1 minus e to the xi beta over 1 plus e to the xi beta. Well, I can simplify this down. How do I do that? I've got e to the xi beta over, I'm going to call this squiggle for a second, and you'll see why soon. Now, if I take the denominator here, I've got 1 minus this fraction. So let's get a common denominator for both parts of this. Then I could write 1 as 1 plus e to the xi beta over 1 plus e to the xi beta. And then subtract off e to the xi beta over 1 plus e to the xi beta. So what's that going to leave me with? That's going to leave me with 1 over 1 plus e to the xi beta, which I'm writing with the squiggle. Notice those 1 plus e to the xi betas, I have that as the denominator of my fraction both in the numerator and the denominator of this larger fraction, so those guys will cancel out. And now I've got e to the xi beta over 1, so this is just ln of e to the xi beta. Well, natural log and e will also cancel out, and now I've got xi beta. So what do I find here? I find that g of g inverse of xi beta gets me back xi beta. That's what I want. That gives me that these are the correct inverses. If I wanted to put the k's back in here, it's going to get a little ugly on me because I have to move them through the ln. So let's not worry about it too much. Let's just say that, let's go way back up here and say that the expected value for this particular case is ki g inverse of xi beta is equal to ki pi, and that should solve our notational issues. Okay, so coming back down here, I've shown that these guys are what I want them to be. Now, I said that this is the first of the common link functions that we use for relating xb to p in binomial regression. What are the other ones that we use? I'm not going to spend nearly as much time on this. On these two, we don't. On the other two common ones, we don't use these as often because there are some nice properties to the logistic, but you may well see these in what you do. So the second common option for a link function is something called the Probit link. And to understand the Probit link, well, let's just go back up here for a second and look at that graph. I said that the logistic function is what we call a sigmoid function. Now, if you've been taking probability and statistics for a while, you might recognize that we have another type of function that commonly looks like this. The other type of function that commonly looks like this, that's a sigmoid function, is a CDF, a cumulative distribution function. So remember, the properties that we like on these sigmoid functions is that as you go negative, this sigmoid function gets closer and closer to returning a 0. As you go positive, this sigmoid function gets closer and closer to returning a 1. And a CDF is going to behave very similarly. For lower values on the x direction with the CDF, we have a lower and lower probability of success. For higher values on the x function, we have a higher and higher cumulative probability of success. So the Probit link uses the standard normal CDF function to model relationship between x beta, xi beta, and our binomial probability P, or PI. So what is this going to look like for us? Well, we have a need for this G inverse and G again, right? So G inverse is going to take xi beta and it's going to turn it into a probability. And then G takes the probability and we'll reverse that back to an xi beta. So G inverse of xi beta gets us the probability. Now, probability is just going to be, we have a nice symbol for the CDF of a standard normal distribution, and that is a capital phi. And so I'm going to use capital phi of, let me take a look at something to make sure I've got this right. Okay. Capital phi of just xi beta. So I'll take my xi beta, I'll plug that into the sigmoid function for a standard normal distribution, and that will return a probability for me. How do I write the inverse guy here? G of pi? Well, this is a little unfulfilling, but I just write the inverse of the cap phi function for that probability, and that moves me back to xi beta. You guys know what the PDF for a standard normal distribution looks like. The CDF doesn't have a nice closed form, which is why we have a symbol for it. There is no good way to write this other than with these symbols, so just know that this is how I express the Probit link function. And the last binomial link function I want to talk about is something called the complementary log-log link. And let me write it down on the next line. That's the proper way of referring to this. Sometimes you'll hear it referred to as the clog-log link function, complementary log-log link. So how does this guy work? I'm going to give you G of pi here because it makes the name of this make a little bit more sense. So what is G of pi? G of pi is natural log of minus natural log of 1 minus pi. And that gets us back to x beta. So, but it's not a particularly nice formula here. But if we think about what p has to be, so p has to be some number between 0 and 1, right? Which means that this is the natural log of some number between 0 and 1. The natural log of some number between 0 and 1 is going to be e to a negative power. The natural log of some number between 0 and 1. A number between 0 and 1 is going to be equal to e to a negative power. So this is going to take out that negative power. And then I'll negate that negative power to make it positive again. And then I will take the natural log of that positive number, which is why this is going to remain valid. And then that gets me my x beta. What is the G inverse function here? The G inverse function on xi beta that gives us back the probability. This is going to be 1 minus, and I've been writing e. I'm going to switch over to exp here, the exponential function, just because it's going to make this a little bit easier to write. 1 minus e to the minus e to the xi beta. And so if I take these guys and do what I did earlier on the logistic, the logistic and the logit, I should find that these are proper inverses of each other too. And if I do g of g inverse of xi beta, I get back xi beta. Because I don't really use the complementary log-log link much, I'm not going to bother deriving that for you. If you want to, go ahead and have fun if you want to do it yourself. But this is what I wanted to talk about for the moment on binomial regression. Just how do we deal with binomial data on a regression model? So if we've got yi, distributed binomial ki pi, and xi being covariate vectors, then we're going to use generalized linear models. We need an exponential family of probability distributions, which is going to be our binomial family of probability distributions. And then we need to be able to relate x beta to the expected value of our binomial response data. We relate x beta to the expected value of our binomial response data through this setup that I have here in number 3. E of yi given xi is going to be ki, the number of random trials involved with yi, times g inverse of xi beta. G inverse of xi beta is something that I will call pi, the probability of success on any particular trial. And then I've got 3 common options for finding that pi. I've got the logistic option for finding that pi, where I use the logistic function, e to the x beta over 1 plus e to the x beta. Or the next most common option is the Probit option, where I just take the CDF of a standard normal applied to x beta. Or I can have this complementary log-log setup where pi is equal to 1 minus e to the minus e to the x beta. Now, obviously, x beta is going to mean something a little different in each of these models. One of the reasons we like the logistic model is that x beta is most interpretable in the logistic model. And I'll talk about that in another lecture at some point. But the betas that you're estimating under the logit, the probit, and the complementary log-log link models, those betas are going to be different in every case. In every case, we're still going to have the situation that I described some up here looking at the logistic model, where I've got e to the x beta hanging out in both this and the complementary log-log model. And the probit model is going to behave similarly. So x beta, if it gets very large or very small, is going to skew probabilities towards 0 or 1 in a hurry. But the particular choice of beta that we estimate in any model is going to depend on the choice of link function that we've got on that model. So it's not like these are directly transferable. But because of this nice setup that we've got with the logistic function and the logit function, where the logit function is the log odds, we can take our betas, and like I said, I'll show this in another lecture here. We can take our betas and we can interpret them pretty directly in terms of the data, which is one of the reasons why the logistic, the logit model, is the one that I tend to favor, because, like I've talked about before, I tend to prefer to put all of my analyses in terms of the data, in terms of possible response observations, because it's usually easier for non-statisticians to understand what a statistical model says in terms of the predictions it makes rather than the parameters hanging out in the middle of that model. I think that's about all I have to say about binomial regression right now. And so my next lecture, I expect, will be about taking a Bayesian approach to binomial regression and where I can bring Bayes in on this generalized linear regression type model.